Alright, so let's introduce our second circuit element in detail, and so that's going to be the resistor. So fundamentally, what is a resistor? Well, it's a device that opposes current flow. So the fundamental relationship that defines a resistor is Ohm's law. And so what Ohm's law tells us is that the potential difference across a resistor is equal to the current through a resistor times the resistance of the resistor. So what is this sort of telling us? Well, again, mostly what it's telling us is that the resistance basically tells you, how much current you're going to get over a particular potential drop. So if you've got a potential across your resistor and you have a very high resistance, then you're actually going to get a small current. So the larger the resistance, so if you fix the potential across your resistor, the larger the resistor is, the smaller the current will be that runs through it. There's sort of two types of resistors that you can run across. One we tend to call ohmic, the other we call non-ohmic. And again, the only difference between an ohmic and a non-ohmic resistor is basically whether R remains constant as you change the potential across the resistor. So for ohmic resistors, right, so things that basically hold a constant value of resistance, it means that as you increase the potential across your resistor, the current increases proportionally with that. So for ohmic materials, when you plot the voltage versus the current, so again, you can think of this as, hey, this is just the equation for a line, y equals m, the resistance is your slope, x, that's what's on our x-axis, plus b, the y-intercept is 0, which is why this goes through the origin. So when we, on a plot of voltage versus current, the slope of the resistance is constant for ohmic materials. For non-ohmic materials, it changes. So this value, or this equation, our fundamental equation, still applies. It applies at all points. It's just that the value of R is different based on which particular point on the curve that you're picking. So this is a non-ohmic material. This is what the curve looks like basically for something like a light bulb. Again, light bulbs are non-ohmic. The resistors that you would play with in physics lab, those are ohmic. They have a particular value, so when it says, hey, you've got a 100 ohm resistor, that's telling you that you have an ohmic resistor because that value doesn't change. Now in terms of units, well, thinking about this equation right here, the units of resistance are going to be equal to the units of potential, volts, over the units of current, amps. So sure enough, volts per amp, that's one way to write the units for resistance. Of course, we've given that another name that happens to be the ohm. So the capital omega is the symbol we use to talk about the units of resistance. All right, so in the same way that we said for capacitors, the capacitance of a capacitor basically depends on the geometry, and then you can talk about the material in terms of whether or not you choose to put a dielectric within your capacitor. Same thing here. The resistance of a resistor depends on the geometry, and it depends on the material you make the resistor out of. So the resistance can be calculated this way. So rho here is the resistivity of the material. It happens to be 1 over sigma. Sigma we've talked about before in terms of our relationship between the electric field and the current density. Sigma is the conductivity. So those two things are inversely related. So you can think of them as the better a material conducts electricity, right? That means the less resistive it is. So the better the conductor it is, the less resistivity you have, because those things are inversely related. So rho here is telling you about the material. L and A are again telling you about the geometry. So the length of your resistor, that's L. The area, here we happen to have a cylindrical resistor, so this area is just the area of a circle. But so this is the length of the conductor and the cross-sectional area of the conductor, the other two factors. And again, the longer you make it, that increases the resistance. The narrower you make it, again, the narrower you make it also increases the resistance, right? So if you've got a narrow conductor, that's more difficult to get current to flow through. And again, here's our symbol for resistor when we do our circuit diagrams. All right, so fundamentally what we tend to care about with a resistor is going to dissipate the energy provided to it. So what that means is usually it'll end up dissipating that energy through what's known as Joule heating, but basically it's just most resistors or many resistors heat up as they resist current flow. And so that energy that's being provided, the electrical energy that's being provided by the battery and by the current is basically being dissipated, turned into some other form, like say heat, or in the case of a light bulb, heat and light. And so the rate at which that energy is being dissipated is given by this equation. So the power is equal to the current times the potential across it. So this is the current through your resistor, this is the potential across your resistor. Again, since Ohm's law tells us that V equals IR, well, if I plug in IR for V here, then I'm going to get I squared times R. So this is just a second way to calculate the rate at which energy is dissipated. And then again, if V equals IR, then I is V over R. So when I plug in V over R for this I, now I have a V squared over R. So all three of these are just basically just taking our definition, P equals IV, and then using Ohm's law to get two other variations that are useful in terms of, well, what of the three things do you know? Do you know the current, do you know the resistance, or do you know the voltage?